Hey nerds, energize. One word and Captain Kirk vanishes from the transporter pad in a shimmer of light and reappears on a planet below. Now, for over 60 years, Star Trek's transporter has been the gold standard of fictional teleportation. Beam Me Up Scotty is so embedded in pop culture that pretty much everyone assumes the future will have teleporters. It's the ultimate transportation fantasy. But is it in our future? Now, physics does have teleportation, like real working, demonstrated in the lab teleportation. It's been around since 1997, and it is an important tool in quantum information science, basically quantum computing. It's just not human level teleportation. Now, today we're going to dive into the physics of teleportation, of course, why quantum mechanics allows us to teleport information under really strict conditions, and why scaling that process to anything larger than a single particle just doesn't really work. Spoiler alert, sorry. We also need to talk about how much information you'd actually need to describe a human being, what the Heisenberg uncertainty principle has to do with Star Trek's Heisenberg compensators, and why even if you solved every measurement, transmission, and reconstruction problem, you'd still be left with a pretty major identity issue. Before we get started, I'm Abby. I'm a physicist at the University of Oxford, currently writing up my PhD thesis. Actually, as you're watching this, I am going to be in Michigan working on one of my thesis experiments using the Zeus laser, which is the most powerful laser in the United States. Now, I love to use sci-fi and pop culture to help explain difficult topics in science, and if you like that kind of stuff, then you should subscribe. And if you are already subscribed to me and you want more content each month, or you just want to support what I'm doing, then you can sign up for a YouTube membership, or you can check me out over on Patreon. I really do appreciate all of the support that you guys give me, and I love getting to know what kind of stuff you're into and what you want me to talk about. Now, I wish that I would be able to teleport home from Michigan, but I'm gonna have to get on a freaking plane just like a regular old muggle. Let's start with what science fiction thinks teleportation is supposed to look like.
Energize.
Teleportation is a very old idea. It shows up all the way back in folklore and mythology as like magic systems where characters disappear from one place and reappear in another with no travel in between. Now, science fiction eventually borrowed the same idea and then tried to give it a technological explanation. And most versions settled on some variation of the same template. Basically, scan the person, send something, rebuild them elsewhere. Now, Star Trek is of course the most recognizable version of this, but I maintain that the first on-screen teleportation device was actually in Doctor Who, Keys of Marinus with the OG Hartnell. Now, if there's something earlier than this, then please do let me know, but that's the earliest one that I have seen on screen. Anyway, transporter in Star Trek. You stand on the pod, the system scans you, it converts you into what the show calls a matter stream, and then sends that to the destination and reassembles you out of something. Now, over the years, they added extra pieces like pattern buffers and, of course, the Heisenberg compensators, which we will come back to later. But the big question here is, are you sending the matter, or are you sending the information about the matter? Now, the original matter stream implies a beam of particles, which leads to a pretty big problem. You see, matter is made of atoms, and atoms interact with other atoms. That interaction, like electrons repelling electrons, it's the reason you can't walk through a wall. And it's also why you can't simply beam a particle stream through like the ship's hull and down to the surface. Every atom would collide with countless others on the way, and most of these interactions would actually scatter the atoms, or they might be absorbed. So basically, none of them would arrive in anything like the correct order. Now, as a physical process, a matter stream isn't going to survive contact with real atoms in real space. So the original idea just doesn't work. Now, Later, it's true, Star Trek sort of shifts towards an information model instead, where your body is scanned, converted into a detailed pattern, and then reconstructed.
I don't think I'm quite ready to have my molecules compressed into a data stream.
They claim it's safe.
Do they indeed?
But the show never addresses the basic issue that reconstruction requires, and that is material at the location. A source of actual atoms to rebuild you from. Basically, they need like a transporter pad on the other side too, not just randomly landing in the middle of a planet or like on the surface of a planet. But there is a movie that has a more scientific approach to this, and that is The Fly. Brundle's telepods operate on data transmission. The system analyzes you down to some level of atomic or molecular detail, sends that information to the other pod, and then rebuilds you using available matter stored in that pod, I guess. Unfortunately for Brundle, like a fly enters and the system can't actually tell the difference between the different biological material, so we get Brundle fly. But the idea posited in The Fly, which is like from 1986, I think it is much closer to what we actually talk about when it comes to real teleportation in physics today, which was only first discussed and demonstrated in the 90s. Now, there is a bunch of other examples across science fiction, of course. One of my favorites actually is, Stargate's ring transporters. Vroom, 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 vroom. Thingy. It's one of my favorite like actual visions or versions of teleportation in sci-fi. But there's also a bunch that we see in like fantasy or like superheroes, Nightcrawler and a bunch of different like magical systems. But they all do one of two things. You either move the matter or you move the information. Now for this video, we are going to focus on the information transfer model because it's the only one that even like vaguely resembles something physics can actually analyze or do. And this is where real teleportation comes in. Because quantum mechanics does allow you to transfer information under very specific conditions.
Energized.
The teleportation that we can do is quantum teleportation. Now, it doesn't move anything physically, it moves information. Specifically, it moves the quantum state of a particle from one location to another. The particle itself stays exactly where it is. Nothing physical travels between the 2 points, just the information. Now, to really get into this and why it doesn't help us build a Star Trek transporter, we need to talk about what a quantum state actually is. Now, in classical physics, describing something it's pretty straightforward. You can measure where it is, you can measure how fast it's going, maybe measure its temperature. These are all definite values and you can write them down as specific numbers. In quantum mechanics, things are different. A quantum state is a complete mathematical description of everything you can know about a quantum system. The quantum state is a full set of information that predicts how the particle will behave. If you want to recreate that behavior somewhere else, you need the entire state. For an electron, that includes things like its spin, its position, its momentum, its phase relationships with other quantum systems. The challenge with this is that these properties don't have definite values until you measure them. An electron doesn't have a fixed position and momentum. These values exist as a superposition. This just means a mathematical combination of multiple possible outcomes. We can also call them probability amplitudes. So you have to measure it to know which value it has, and measurement changes the state. When you measure an electron's position, you get a definite answer, but you also irreversibly change the system. The quantum state after the measurement is not the same state as the state before the measurement. I've been trying to think for ages of a good way to try to describe this, and one of the things that I've come up with is imagine a grid of squares, okay? Each square is labeled with a random place name, but the names aren't visible to you, and any square could have any one of the possible names available. Now, say there's a person standing on one square. The only way to find out where they are is to push them off the square. That action causes the place name on the square to light up so you can see it. You've got the definite position, but the person's no longer standing on the square. They're now on a different square. To find out their position, you had to interact with them in a way that changed it. That's why you can't just read a quantum state without consequences. The act of measurement fundamentally changes what you are measuring. So, when physicists say they've teleported a quantum state, they mean that they have transferred all of this information, the superposition, the phase relationships, the probability distributions, they've transferred all of that from one particle to another particle without ever directly measuring what the information was. They don't know what the state is. They've just sent it somewhere else. You see, you can't measure all of these properties at the same time. The uncertainty principle forbids this. But quantum teleportation doesn't actually need for you to know what the state is. Through entanglement and a special measurement, the Bell measurement, you transfer the state intact, never learning the details of it. The original state is destroyed in the process, but it reappears at the destination with all its quantum properties preserved. Now, the particle doesn't appear, just the state it was in. So let's go through how this all works.
Energized.
Now, a method for quantum teleportation was first proposed in 1993 in the paper Teleporting an Unknown Quantum State via Dual Classical and Einstein-Podolsky-Rosen Channels. It was first demonstrated then experimentally in 1997 by two separate groups, led by Sandu Popescu and Anton Zellinger, who later went on to win a Nobel Prize. Both of them were using photons. Now, the method relies on three key ingredients: entanglement, Bell state measurement, and classical communication. So, let's say that you want to teleport the quantum state of particle X from Alice to Bob. Step one, we need to create entanglement. The first thing you have to do in any of these experiments is create a pair of entangled particles, A and B. Entanglement means that their quantum states are correlated in a specific way. Basically, you know the combined state of the pair, but you don't know what their individual states are, and neither particle will have its own definite state until you measure it. So Alice keeps particle A, and Bob takes particle B off to some distant location. The entanglement between them stays no matter how far apart they are, not because there's any signaling happening between them, but because they were prepared together in a single correlated state. The next thing you have to do is a Bell state measurement. So Alice now has two particles. She has particle X, the one whose state she wants to teleport, and she has particle A, which is her half of the entangled pair. She performs a special joint measurement called a Bell state measurement on X and A together. Now, this does two things at the same time. First, it destroys the original quantum state of particle X. You can't make a copy of an unknown quantum state. Any attempt to extract complete information about it must destroy the original. And the second thing it does is it projects Bob's particle B into a state that is mathematically related to the original state of X, but not exactly the same yet. You see, Alice's measurement will have four possible outcomes. So Bob's particle ends up in one of four related states. And this is why classical communication is important, because the next step is when Alice's measurement gives her two classical bits of information, and this is what tells her which of the four outcomes has happened. She then sends those two bits to Bob by ordinary communication, phone, radio, fiber, like whatever. This step cannot be faster than light. Without Alice's message, Bob just has a particle in some unknown state. Only after he receives her two bits and knows which outcome she got can he complete the teleportation process. This is why quantum teleportation doesn't violate relativity. Entanglement correlations are there, but you still need a classical signal to do anything useful with them. So the final step, quantum operation. Bob receives Alice's 2 bits. He applies a simple quantum operation to his particle B, like it could be a rotation or a flip, depending on the message he got from Alice. After doing this correction, particle B is now in exactly the same quantum state that particle X originally had. Teleportation is complete. X's state has been destroyed at Alice's location and recreated at Bob's. The particle never moved. Each teleportation event moves the state of one particle or one simple quantum system. Doing this for something the size of a molecule, never mind a human, means dealing with an astronomically complicated many-body state. And that last point is where our transporter problems really begin. Even if quantum teleportation works perfectly for single particles, and it does, absolutely, scaling it up to anything macroscopic runs into limits that unfortunately are not about engineering.
Energized.
Quantum teleportation works beautifully for single particles like photons or electrons. Even individual atoms have teleported in lab conditions. It works exactly as suspected for these types of systems. A human body is not that kind of system. Our bodies contain about 7 times 10 to the 27 atoms. That's 7,000 trillion. But the important point isn't really the number here, it's how the atoms behave. Because they're part of this enormous, interacting, constantly changing quantum system. You've got chemical bonds forming and breaking. We have ions moving across cell membranes. Proteins fold and unfold, or neurons switch their electrochemical states. Any thermal motion shakes every atom on timescales down to femtoseconds. That's a millionth of a billionth of a second. To teleport a person, you would need a complete description of that entire system at one instant in time. And that's where all the problems start. Teleportation only works if the sender and receiver share entanglement in advance. For a single photon, that means one entangled pair, one particle with Alice, one particle with Bob. For something human-sized, you would need the equivalent of matching entangled partners for essentially everything that matters to the state. And by the state, I mean the entire functioning of the human body. Now, experiments today can create entanglement between thousands of atoms in very controlled conditions. But that entanglement is extremely fragile. Any interaction with the outside world, like a scattered photon, a simple vibration, a tiny bit of thermal motion, that leaks information into the environment and destroys the quantum correlations. And that process is called decoherence. Now, you might be thinking, well, how does it work in a quantum computer then if they're so fragile? Well, they're cooled close to absolute zero. And even at that, they might keep coherence for only like milliseconds. In a warm, wet, biological tissue, electronic states decohere in femtoseconds. The quantum information you would need to teleport just does not stay in a clean, usable form for long enough to do anything with it. And another issue here is that a human being isn't a lot of particles in a row. The correct description is one huge quantum state that includes all the particles and all of the relationships between them. The process for quantum teleportation assumes that you have this well-defined system whose state you can treat as a single thing, the state of this atom. In a living body, you cannot cleanly separate out the state of atom number 1 and then the state of atom number 2 as independent pieces to send one by one. If you try to break the system into parts, you just lose the structure that you're trying to record. But, you guys, we're going to be generous. We're going to imagine that we could somehow keep all that quantum information intact. Well, the next step in any scan and rebuild teleporter is obvious. You got to scan the person. To rebuild someone from scratch, you would need to know where every atom is and how fast it's moving. And that's where Heisenberg's uncertainty principle steps in and says, no.
Energize.
The principle tells us that position and momentum are not things that you can know at the same time with unlimited precision. It's not that our scanners are too weak or that our detectors are too slow or anything like that. Quantum mechanics itself doesn't allow a particle to have a perfectly sharp position and a perfectly sharp momentum at the same time. If you measure position very precisely, momentum gets really fuzzy. If you measure momentum really precisely, position gets really fuzzy. This trade-off is built into the mathematics. But to recreate a person, you would need to know both pieces of information for every single atom in the body perfectly recorded. And unfortunately, that perfect set of values just doesn't exist. Now, Star Trek at least acknowledged this and invented Heisenberg compensators. These are fictional devices that just make the uncertainty go away. Now, it's a nod to the physics saying no while the plot still needs a yes. In reality, there is nothing to compensate. You can't engineer around the uncertainty principle, not any more than you can engineer your way to infinite energy or faster than light communication. Someone's going to argue me on that point, but I've already explained entanglement, you guys, don't use it. But I am generous. You know I am. You know I'm generous with the sci-fi. So suppose we live in a universe where compensators exist and we can measure everything precisely. How would we actually do the scan? So, this is a pretty big issue for our teleporters. The measurement destruction problem.
Energize.
To find out where something is, you have to interact with it. Now, in our everyday lives, that usually means using light. So you fire photons at something and a bunch of them scatter off and you detect them, and that tells you something about the object. To see small structures, you need light with a wavelength that is comparable to the structure. Now, atoms are about an angstrom apart, and that's 10 to the minus 10 meters. To resolve details at that scale, you need light with wavelengths that small. Short wavelengths mean high energy photons. So we're talking X-rays or gamma rays. X-rays and gamma rays have enough energy to strip electrons from atoms, break chemical bonds, and dump heat into whatever they hit. A full body scan that is trying to record atomic positions everywhere means that you would be blasting every atom in your body with high energy radiation. The total energy dumped into your tissue would tear molecules apart and heat everything far beyond any level you could survive. You would be destroyed long before the scan finished. This isn't about building a better scanner, you guys. It's how measurement works on these scales. The sharper the image, the more energy you have to throw at the object. At atomic resolution, that energy is just destructive to us. Now, this is probably what's happening in The Fly, right? Because Seth Brundle steps into the telepod, the system scans him in enough detail to rebuild him, and that scan cannot be gentle. But that's not going to stop us, is it? We're going to keep going. We're going to imagine some magical future scanner that can get around the destruction problem. So now we need to talk about timing.
Energize.
All right, so we've somehow solved all of this. We have perfect entanglement for everything. We have no decoherence. We have a scanner that doesn't destroy what it measures. We have no trouble with the uncertainty principle. Just assuming that all of that is sorted out. Quantum processes in matter happen on extremely short timescales, femtoseconds, even attoseconds, some even down to zeptoseconds for the fastest electronic motion. So let's be wildly optimistic and assume that we can measure one atom's complete state every zeptosecond. Now, there are 10 to the 21 zeptoseconds in 1 second. For the 7 times 10 to the 27 atoms in our body, that gives us about 7 million seconds of scanning, roughly 81 days of continuous, perfect, uninterrupted measurement. Now, I'm sure you're going to object that we would not scan one atom at a time. Of course not, that's dumb. We would scan them all simultaneously. Fine, sure. But that means capturing, processing, and storing an unimaginable amount of data in a single instant. And that moves us into a different set of limits. How much information a human actually contains, how much storage you would need, and how long it would take to transmit. So that's where we're going next.
Energized.
You guys, even if we forget the quantum complications for a minute, right? Just try to rebuild a person at like a classical atomic precision. The amount of information you would need is still enormous. To describe a human being, you have to describe roughly 7 times 10 to the 27 atoms. And for each atom, you need enough information to put it back exactly where it was and with all the chemical context that makes biology actually work. Now, in information theory, the number of bits you need to specify one choice out of n possibilities is log 2n. So if an atom could be in a trillion different positions, you need about 40 bits to say which one it's actually in. So here's a rough breakdown of what we would need per atom. Starting with position, okay? The body is about a meter across. An atomic precision, as we already learned, is around an angstrom. So that's about 10 to the 10 possible positions along each axis. And we have 3 axes. So 33 bits per axis gives us about 100 bits for the full 3D positioning in the body. We also need the momentum, and this is to preserve the dynamics, like how everything is moving. And that's about like the same precision as the position one, so that's another 100 bits. We need the element identity. Now there are about 100 possible elements, so that's 7 bits. And then we need chemical structure, like bond partners, bond types, bond angles. For a typical atom, this is about 50 to 100 bits. Electronic configuration as well, which orbitals are filled, approximate energies, that's another 50 to 100 bits. So altogether, a very conservative classical estimate is roughly 400 bits per atom. Multiply that by the 10 to the 27 atoms, you get 3 by 10 to the 30 bits. That is a 3 followed by 30 zeros, 3,000 billion bits. That is the amount of information needed just to describe the arrangement, not the quantum state or like the chemical environment or any biological processes happening on top of that, just a very, very rough structural blueprint for your body. So how big is 3 by 10 to the 30 bits? Well, for context, in 2025, it's estimated that the Earth will generate about 1.5 by 10 to the 24 bits of data. So your body contains about 2 million times the amount of data that the entire planet of Earth can generate in 1 year. So for us to store one human being, we'd need every byte of global data production for the next 2 million years, or we would somehow need to increase Earth's entire storage capacity by a factor of 2 million, and then dedicate it all to like scanning one person. Before someone in the comments starts saying, well, storage will improve, because I know you're gonna, remember, storage requires materials. Data centers take power, they need cooling, they use metals, there's fabrication, land maintenance. There is no magical future where we scale storage by factors of 1 million without hitting physical and economic limits. And this is still the classical estimate, you guys. We're not even touching quantum information here. But we're going to keep going. Because let's say you've stored all the 3 by 10 to the 30 bits. Well, now you need to send it. The fastest fiber optic systems ever demonstrated move about 10 to the 14 bits per second. Now, this is experimental lab-grade performance. This isn't like slow commercial stuff. This is the best of the best. At that speed, transmitting the information in one human body would take, drumroll please, about 950 million years. Nearly 1 billion years of continuous transmission. Even if future tech is much faster, communication channels have hard physical limits, noise, bandwidth, capacity, and the sheer power required to push information at higher speeds. Which brings us to the unavoidable energy bill. You guys, it nearly always comes down to energy. I really think we're going to have to talk about energy soon. We're going to have to talk about resources and limits and like what we can even hope for the future. But we'll get to that eventually in another video when you guys vote for it in the poll.
Energized.
Now, you may or may not know that information isn't free. There's this thing called Landauer's principle, and it tells us how much energy information costs. The formula is E equals KT ln 2. That's the natural log of 2. So processing or erasing a single bit costs at least 3 by 10 to the minus 21 joules. Now, that doesn't sound like much, but when we're talking about the amount of bits that we need, that's the equivalent of 300 litres of petrol. And that's the absolute theoretical minimum allowed by physics. This isn't the actual cost of the process. This is the minimum cost of simply handling the data. We still have to add inefficiencies, cooling, error correction, scanning, transmission losses, and the actual reconstruction process of the human body. You can't engineer your way out of this. The cost comes straight from the second law of thermodynamics. The information requirements alone makes teleportation impossible for anything that we currently have and likely for any future ideas due to energy and resources. Some of you are going to argue me on that. Some of you are going to be very upset with me for saying impossible. People get very hung up on that. You should never say impossible. Physics, you never know what could happen. You never know what could happen. There is still limited resources in the universe, you guys. So unless you can completely break the entire laws of physics and create an entirely new universe, I don't see how you're getting around this. But I know you want to break it. So let's continue being extremely generous to science fiction. Let's pretend infinite storage exists, and instant transmission exists, and reconstruction is completely fine and easy. Even if you granted all of that, you still run into one final question that physics can't help us with.
Energized.
Quantum mechanics has a rule called the no cloning theorem. It says you cannot create an identical copy of an arbitrary unknown quantum state. Now, this isn't anything to do with technology or anything like that. It's a mathematical impossibility. And it matters for teleportation. Because if you could just like read out a quantum state perfectly without disturbing it, you could copy it. You measure the state, you write down the result, and then you use that information to create a duplicate while leaving the original intact. Well, we know this isn't possible. The no cloning theorem says you can't do that. Any process that extracts complete quantum information has to destroy the original state. Real quantum teleportation respects this. The Bell state measurement destroys the original quantum state at the same moment that it is transferring the information. At no point do two copies ever exist. You can move a quantum state from one system to another, but only by erasing it at the origin. And that brings us to the final question. If the original is destroyed and a perfect copy is created somewhere else, is it still you? The original has been destroyed. Every atom, every molecule, every neural connection has been disassembled. The reconstruction is perfect. Same atomic positions, same chemical bonds, same memories. That's an entirely different issue. We won't get into that now. Same personality. From the outside, there's no difference. The reconstructed person would remember stepping onto the teleporter pad, remember their entire life, and be completely convinced that they survived the journey. But are they you? This is an old question. The ancient Greeks asked it about a ship, the ship of Theseus. If you replace one plank, it's still the same ship. Replace another, still the same. Keep going until every plank has been replaced. Is it still the same ship? Now, your body does a version of this all the time. Atoms are constantly replaced through metabolism. Cells die and are rebuilt. Most of the molecules that make up your body like 10 years ago, they're all gone. Yet you still feel like the same person. The crucial difference here is continuity. In biology, your atoms are replaced gradually while your consciousness carries on. Your neural activity never fully shuts down. There's an unbroken chain connecting you now to you 10 years ago. Teleportation breaks that chain. You are completely disassembled. For some period, however brief, you do not exist. Then a new person, atom for atom, identical to you, is assembled somewhere else. Now, one way to think about it is teleportation doesn't move you, it kills you and recreates a perfect copy. Everyone who knows you would accept that person as you. The copy would have no doubt they survived. From their point of view, they stepped onto the pad, there was a moment of weirdness, and then they stepped off. Somewhere else in the universe, they traveled and they're happy. But from your perspective, the original standing on the pad, what happens? Do you experience stepping off at the destination? Or do you experience being destroyed while someone else with your memories opens their eyes on the other side? The thing is, we don't know, and we can't know, because consciousness, which is that subjective feeling of being you, that's not something that we have a scientific explanation for. Now, some people will argue that identity is about pattern, not material. So if the pattern is preserved, like all the information that defines you, then you survive. It doesn't matter if it's the same atoms or if it's different atoms, as long as the structure is the same. Others will argue that consciousness requires continuity, that there is something about the ongoing process, the unbroken stream of neural activity, the continuous thread of experience, saying that you can't pause, copy, and restart without losing you in the middle. Both positions are internally consistent and neither can be tested with current science. So physics can tell us whether teleportation is possible. For single particles or small systems, yes it is. For full human bodies, no. Not with any physics that we understand or can reasonably extrapolate to the future. But even if it were possible, physics can't tell us whether you would survive it. That question is about consciousness and personal identity, not about quantum states and information. So even in the most generous hypothetical, magic solves measurement, storage, transmission, and reconstruction, we're still left with an unanswerable question. Is stepping into a teleporter like walking through a door, or like walking into an execution chamber that builds your replacement on the other side? Look, the truth is, Star Trek needed the transporter for practical reasons. Getting actors on and off planets every episode using the shuttle would have been expensive and time-consuming in the 60s. The transporter was created as a budget-saving plot device, but it became something more. This vision of the ultimate convenience, the ability to go anywhere instantly. Now, as I said, Star Trek didn't invent this idea, and I really don't want to overly focus on Star Trek every episode, but it really did shape how generations of people think about future technology. Science fiction doesn't have to be realistic. I am so fine with it not being realistic, but it has to be dramatically satisfying. The transporter works because it enables stories, not because it respects like quantum mechanics, even with the Heisenberg compensators. The interesting part for me personally is seeing where fiction meets reality. That's why I make these videos. Every impossible piece of technology reveals something to us about how the universe actually works. Warp drive taught us about space-time and causality. Artificial gravity taught us about the equivalence principle and centrifuges. And teleportation shows us the fundamental limits of measurement, information, and the quantum nature of reality. Now, could we be wrong? Could future physics overturn everything we think we know? Sure, of course, come on. Science continuously updates. That's the beauty of it. It's what it's there for. We learn new things, and so we change our views and our approaches. But like many things we talk about on this channel, it would require rewriting everything we know, and that is a really big ask. So for now, and for the foreseeable future, the transporter remains what it always was. Fun science fiction, impossible science. Now, I am genuinely sorry to kill your dreams. It's not my intention. While we can't step onto a pad and reappear on another planet, we can at least understand why we can't. And I hope that that's enough for at least some of you for now. Thanks for watching. Stay nerdy. Oh, I wish I had a little like Star Trek science officer's pin. Where can I get one? All right.
Energized.